Hello friends, so today we are going to solve the questions from the chapter Heat and Thermodynamics. In this we are going to solve the questions from the year 2023. We are going to solve total 19 questions, and all these 19 questions are from the mains. And from the year 2023, this is part 1. So the first question, it states that the number of air molecules per centimeter cube increased from 3 into 10 to the power 19 to 12 into 10 to the power 19. The ratio of collision frequency of air molecules before and after the increased in number respectively is. So here we have to find out the ratio of the collision frequency before and after. And we know that our mean free path, which is given as lambda, so we have mean free path, which is lambda. It is given as 1 upon square root of 2 pi d square and n. So from here we can see that our lambda is inversely proportional to our n. Okay. Or we can say and we have to find out the collision frequency, and we know that our collision frequency is inversely proportional to mean free path. So you can say our collision frequency, if it is represented as f, is inversely proportional to mean free path, or we can say that our collision frequency will be directly proportional to our n, where n is our number of air molecules. Therefore we can divide, or we can say we can write the formula in terms of ratio, that the frequency before to frequency after will be equal to number of molecules before and number of molecules after. So we get this as 3 into 10 to the power 19 and 12 into 10 to the power 19. 19 goes away and this 12 goes by 4. So we get this as 1 by 4, which will be equal to 0.25. Okay. So option number 2 is correct. Next question. It states that the temperature of an ideal gas is increased from 200 Kelvin to 800 Kelvin if r.m.s speed of gas is 200 Kelvin is V0, then r.m.s speed of the gas at 800 Kelvin will be. So this is based on directly the formula. We know that our r.m.s speed for ideal gas, that is V_r.m.s, is equal to 3 RT upon m and its square root. where R is the gas constant, T is the temperature, and M is the molar mass. Therefore, we can say from here that our v.r.m.s, because gas is same, only the temperature is different, so value of R and M will be same for the gas, so v.r.m.s will be proportional to us square root of temperature. And we can write the formula for our v.r.m.s at 800 divided by v.r.m.s at 200 will be equal to temperature of 800 divided by temperature of 200. And so this becomes basically 800 divided by 200 its square root and is equal to 2. And we are given that at 200 the velocity is v naught. Therefore, we can say that our v.r.m.s at 800 will be equal to 2 times v.r.m.s at 200. So this comes 2 times v naught. So we have option number 4 is correct. 4 is correct. Next question. It states that the temperature at which the kinetic energy of oxygen molecules becomes double then its value at 27 degrees centigrade is. So the kinetic energy becomes double of the initial temperature, that is 27 degree centigrade. And for that we are going to use the formula, that is our average kinetic energy per molecule. Average kinetic energy per molecule, that is our Ke is equal to 3 by 2 times Kt, where K is the Boltzmann constant and T is the absolute temperature. And we are given that the kinetic energy at a certain temperature T2 was our twice of kinetic energy at the temperature T1, and T1 is 27 degrees centigrade, and in absolute we can write this as our 300 Kelvin. So we can formulate in terms of this 3 by 2 K T2 is equal to twice multiplied by 3 by 2 K, and this is our multiplied by T1. So here this 3 by 2 K and K cancels out, and we get that our T2 is equal to 2 times T1, that is 2 times 300, giving us 600 Kelvin. And in terms of degree centigrade, we can say that our T2 will be equal to 600 minus 273, which gives us 327 degree centigrade. So option 3 is correct. Next question. It states that a gas mixture consists of 2 moles of oxygen and 4 moles of neon at temperature T. Neglecting all vibrational modes, calculate the total internal energy of the system oxygen has two rotational modes. So here we are having two gases, oxygen and neon. Okay, and we have to find out the total energy of the system, which is energy associated with oxygen plus energy associated with the neon. And we know the formula that internal energy of ideal gas of ideal gas, which is suppose our U is equal to F upon 2 nRT. Here F is our degrees of freedom. Okay. And we have a neon gas which is monatomic. So we can see we have our neon which is monatomic, giving us value of F is our 3, and therefore we can write that energy associated with neon will be equal to our 3 by 2. Number of moles of neon are given as 4 times RT, and 4 goes by 2, so we get internal energy associated with neon will be equal to 6 RT. Similarly, we can write for our oxygen also, and oxygen is our diatomic, and here value of our F is our 3. 3 will be our translational and 2 will be our rotational. Okay. And so we get this as our 5. Therefore we get our U for our oxygen will be equal to 5 by 2 times 2. Number of moles are oxygen 2, and this is our RT. 2 cancel with 2, so we get our internal energy associated with oxygen will be equal to 5 RT. So now the total internal energy that is U, internal energy with neon and internal energy associated with oxygen. So this comes as 6 plus 5 times RT, and which gives us the total, let us call the UT, will be equal to 11 RT. Next question. It states that 3 vessels of equal volume contains gases at same temperature and pressure. The first vessel contains neon, which is monatomic. The second vessel chlorine diatomic, and third contains uranium hexafluoride, which is polyatomic. Arrange these on the basis of their r.m.s speeds. Choose the correct answer from the option given. So we have to arrange there how their r.m.s is going to change. Okay. And so in this case, we are going to start with our standard formula, that is our V.r.m.s is equal to 3 RT upon m, which is a molar mass. Therefore from here we can say that our V.r.m.s is inversely proportional to square root of our molar mass. Okay. And if you can say write the molar mass of all the the contents. First one is neon. Neon's molar mass is approximately equal to 20 gram per mole. And we have chlorine, which is having a molar mass of close to 71 gram per mole. And we have our uranium hexafluoride, which is our UF6, and that is having a molar mass of approximately equal to 352 gram per mole. So it means the molar mass of neon is the lowest, so we can say our molar mass of neon is less than molar mass of our chlorine is less than the molar mass of our UF6. So based on this, we can write that our r.m.s for neon will be greater than r.m.s for our chlorine is greater than r.m.s for our uranium hexafluoride. So neon is our mono, so that will be mono dia, and option 2 is correct. Option 2 is correct. Next question. It states that the root mean square speed of molecules of nitrogen at 27 degrees centigrade is approximately, given the mass of nitrogen molecule is 4.6 into 10 to the power minus 26, take the Boltzmann constant as 1.4 into 10 to the power minus 23. So we have to find out the r.m.s speed of the nitrogen molecule. So it is straightforward based on the formula. We simply put the values and get the answer. So we know that our r.m.s is equal to 3 kBt divided by its molar mass. So we simply substitute the values. We get this as 3 times 1.4 into 10 to the power minus 23. T is our absolute temperature, that will be over 300, and molar mass is 4.6 into 10 to the power minus 26 and its square root. So its solution will be approximately coming as 523 meter per second. So option 1 is correct. Next question. It states that if the r.m.s speed of the chlorine molecule is 490 meter per second at 27 degrees centigrade, the r.m.s speed of argon molecules at the same temperature will be, the atomic mass of argon is 39.9 and molecular mass of chlorine is 70.9. So in this case also, we are going to use the formula, that is r.m.s is equal to 3 kT divided by m, and it is said that it is at same temperature. Therefore from here we can say that our r.m.s is inversely proportional to our m. And we can write the ratio respectively for chlorine as well as our argon. Therefore we can say that our r.m.s for argon ratio V.r.m.s for chlorine is equal to, we get this as m for chlorine and m for our argon, and whose values are given to us. So we can say for chlorine it is our 70.9 and this is 39.9 and its square root, and this comes approximately as 1.33, and velocity V.r.m.s for chlorine is given, so we get this as V.r.m.s of argon is equal to V.r.m.s for chlorine multiplied by 1.33. So it is given as 490. So this comes as 490 multiplied by 1.33. Therefore, we get that our V.r.m.s for our argon is approximately equal to 653. Okay. So the closest one is option number 3 is correct. Is correct. Next question. It states that the r.m.s speed of oxygen molecule in a vessel at a particular temperature is 1 plus 5 upon x raised to power 1 by 2 times v, where v is the average velocity of the molecule. The value of x will be. So here it is talking about two velocities. One is r.m.s and other one is of average velocity. Okay. So we know that our r.m.s velocity, which is our v.r.m.s, is equal to 3 kt divided by m, and our average velocity that is, in this case it is given as v, will be equal to, this is our 8 rt divided by pi times m square root, and we are given that r.m.s speed particular temperature is okay. So we are given that our v.r.m.s is equal to 1 plus 5 upon x whole raised to power 1 by 2 times v. So we substitute the value of v.r.m.s as well as v. So this we get as a 3 kt upon m square root is equal to 1 plus 5 upon x whole raised to power 1 by 2 times, and v is our 8 rt one second. Yes. Here it is k. I just put it k, and this is also k, and divided by pi times m square root. So we can cancel this square root throughout, and this gives us 3 kt upon m is equal to 1 plus 5 upon x is equal to 8 kt and pi m. So once again this kt, m and m cancels out. So we get this as our 3 pi and divided by 8. So we can write as this will be equal to 1 plus 5 upon x will be equal to 3 pi by 8, and pi we substitute as 22 by 7. Okay, so we can further solve it. We get this as our 5 upon x is equal to, we get this as our 3 multiplied by 22 and 8 multiplied by 7 minus 1, and this will be equal to our this will be about 66, and here we have having 56. We can just, this goes by 11 and this goes by 4, and we get this as 33. 28 minus 1, which gives us 28, and this comes as 5, and this 5 and 5 cancels out, so we get value of x is equal to 28. So option 1 is correct. Next question. It states that the mean free path of molecules of a certain gas at STP is 1500 times d, where d is the diameter of the gas molecules. While maintaining the standard pressure, the mean free path of the molecules at 373 Kelvin is approximately. Okay. In this case, we are going to use the formula for mean free path, and we know that our mean free path, which is our lambda, is equal to 1 upon square root of 2 pi d square multiplied by n. Here n is the number density. Okay. So n is our number density, and we also know that at constant pressure P will be equal to n times kT, and therefore from here we can write that our n is inversely proportional to 1 by t, and let me put it here. Therefore from this relationship, that is P is equal to n times kT, as pressure is constant, therefore we can say n is inversely proportional to T, and our lambda is inversely proportional to n. So from here we can write lambda is inversely proportional to n, therefore we can say our lambda is directly proportional to T, and so we can write this formula in the form of ratio. We can say our lambda 2 upon lambda 1 will be equal to T2 upon T1, and this T2 is our 373 Kelvin, so this becomes 373, and T1 is our T1 is our standard temperature pressure, which is our 273 Kelvin, and this ratio will be approximately equal to 1.36, and lambda 1. So we can say from here that our lambda 2 is equal to 1.36 times lambda 1, and mean lambda 1 is given to us. Therefore we can say that our lambda 2 is equal to 1.36 times 1500 D, and this approximately will be equal to 2049 times D. So option number 2 is correct. Next question. So it states that a flask contains hydrogen and argon in the ratio 2:1 by mass. The temperature of the mixture is 30 degrees centigrade. The ratio of the average kinetic energy per molecule of the two gases, that is K argon to K hydrogen, is atomic weight of argon is given to us. And so we need to find out the average kinetic energy. So we can say our average kinetic energy per molecule it is a Ke is equal to 3/2 times Kt. And so in particular this equation we clearly see that kinetic energy is dependent only on the temperature T, because K is our Boltzmann constant, so it is going to have the same value. Therefore from here we can say that our kinetic energy is proportional to temperature T. Therefore kinetic energy for the argon divided by kinetic energy for our hydrogen will be equal to temperature of our argon and temperature of our hydrogen, and the mixture is at same temperature, that is 30 degrees centigrade. So this will be 30 upon 30, and even if you take the absolute temperature, the ratio is not going to change much. Okay, so this will be coming as 1. So option 1 is correct. Or we can say directly interpret the result also. Kinetic energy is only dependent upon the temperature, and the ratio is given by mass is 2:1. So there is no you can say mass in the formula for our average kinetic energy. So you can say option 1 is correct. Next question. It states that a source supplies heat to a system at a rate of 1000 watt. If the system performs work at a rate of 200 watt, the rate at which internal energy of the system increases. So for this we are going to use first law of thermodynamics, because we are given that the heat supplied by the source is given as 1000 watt, which is our Q, and work done is also given 200 watt, that is our W. So we can find out our delta of U, and that is rate, so delta U divided by delta T. So we are going to use first law of thermodynamics. First law of thermodynamics, and it gives us that our delta of U is equal to Q minus W, and here is Q, the heat added, which is given to us as 1000, or we can say rate of heat added is 1000. So we can just modify this as our delta T delta T and delta T, minus 200, which gives us 800 watts. So we have option number 4 is correct. Next question. It states that work done by a Carnot engine operating between temperatures 127 degrees centigrade and 27 degrees centigrade is 2 kilojoule. The amount of heat transferred by the engine to the engine by the reservoir is. So for that we can just draw an approximate figure for it. We have our source and this is our engine, and then we are having a sink. Okay. Source is supposed as a temperature T1 and it is going to supply a heat of Q1 to the engine, and this engine is going to do some work. Let us suppose that work is W, and remaining heat is going to Q2 for our sink. Let us suppose that is our T2, and this is basically our Carnot engine, basic one. And we know that our efficiency of our Carnot engine that is our nu is equal to 1 minus, and this comes as our T2 upon T1, and we come this as 1 minus T2 is 27 degrees centigrade, so this will be coming as 300 Kelvin. T1 is 127 degrees centigrade, so that will be coming as 400 Kelvin. Therefore we get that efficiency is equal to 0.25, and the efficiency is also in terms of work done is our W upon this Q2, that is a heat supply to the reservoir, and therefore we can write that our Q2 will be equal to work done upon efficiency, and work done is 2 kilojoule, efficiency is 0.25, so this comes as 8 kilojoule. So we have option number 3 is correct. Next question. It states that consider two containers A and B containing monatomic gases at the same pressure P, V and T. The gas A is compressed isothermally to 1/8 of its original volume, while the gas B is compressed adiabatically to 1/8 of its original volume. The ratio of the final pressure in the gas B to that of gas A is. So two gases, and they are having a different processes. One is isothermal and second one is our adiabatic. So we can say that for our container A, which is our isothermal, and so we can write that our PV is equal to constant, and So we can write it as if PV is equal to constant, and if we assume that the final pressure and volume are PA and VA, therefore we can write this as initial our PV is equal to PA times VA, and the final is given to us as this is A, but we are given that the compressed isothermally to 1/8 of original volume. So original volume is V, so we can write this as a PA, this comes as a V upon 8, and here V and V cancels out, therefore we get that our P will be equal to our PA times 8, or we can say the final pressure in A will be equal to 8 times P. And the second is our B, which is our adiabatic, and for adiabatic we know that PV raised to power gamma is equal to constant, and therefore we can write that a PV gamma is equal to P of our B and volume of our B raised to power gamma, because initially both A and B are same pressure as well as temperature as well as volume. So for initial conditions, that is our left side in both cases is going to remain same, and so we can write this as our PV raised to power gamma is equal to P of B, and the final is our 1/8 of its initial volume gamma. This comes as our V raised to power gamma PB, and it can be written as 1/8 raised to power gamma, and this gas is given to us as monatomic, therefore value of gamma is our 5/3, so this comes as 5/3, and here this volume term cancels out, therefore we can write that our final pressure of a PB will be equal to initial pressure times 8 whole raised to power 5/3, and we have to find out the ratio. So we can say that we have to find out PB to PA. PB to PA is equal to, and this comes as a P 8 raised to power 5/3, and this comes as P multiplied by 8. So here P and P cancel out, and this comes as our 8. 8 will be 5/3 minus 1, which will be our 2/3, and 2/3 cube root will be 2, and 2 square is equal to 4. Therefore we can say that our ratio of our PB upon PA is equal to 4. So option 4 is correct. Next question. It states that an engine operating between the boiling point and freezing point of water will have efficiency more than 27%, efficiency less than the efficiency of Carnot engine operating between the same two temperatures, and efficiency equal to 27%, and the final option is efficiency less than 27%. So based on this we have to check which of the combination makes a true, you can say correct combination. And so let's find out what will be the efficiency of our Carnot engine. So we know that our Carnot efficiency that is when nu will be equal to 1 minus T of C upon T of H, and it is between freezing and boiling point. Therefore we can write this as 1 minus, and it comes as 273 and 373 Kelvin. Therefore the efficiency will be approximately equal to 26.8%. So this is the efficiency of the Carnot engine, and it says that efficiency is more than 27%, so this option is incorrect, and efficiency is less than the efficiency of Carnot engine, and so this will be true for every, you can say, non-Carnot engine. Okay. So this option number 2 will be correct. Efficiency is equal to 27%, which is also wrong, and finally efficiency is less than 27%, so this is correct. So we have option number 2 and 4 are correct, so we get option 3 is correct. Next question. It states that the initial pressure and the volume of ideal gas are P0 V0. The final pressure of the gas when the gas is suddenly compressed to volume V0 by 4 is given by. So in this case it is given that the gas is compressed suddenly, so the process will be our adiabatic process. We are going to use the PV raised to power gamma is equal to constant. So we are given that we have sudden compression and sudden compression basically means that we have a adiabatic process, and for adiabatic process we know that PV raised to power gamma is equal to constant, and so we can write that initial is given as P0 V0 raised to power gamma, and let us suppose final we have our PF VF raised to power gamma, and the relationship between the volumes is given, so this comes as V0 upon 4 whole raised to power gamma, and we can write this as our P0 V0 raised to power gamma is equal to V0 raised to power gamma, and this comes as our PF 1 by 4 raised to power gamma. So this V0 cancels out, and one second. Okay, we need to final pressure, so we get our final pressure will be equal to P0 4 raised to power gamma. So we get option 2 is correct. Next question. It states that a thermodynamic system is taken through a cyclic process. The total work done in the process is, basic PV diagram is given to us, so which is cyclic DECD, and which forms a right angle triangle. We have to find out work done, and the work done for our this on the PV scale is nothing but our area of our loop. can say that work done will be equal to area of the loop. So we can say area of our, we have this as DECD, which is a right angle triangle. So we get this as our half, and base is about 2, and this is our height is 400 minus 300, which is 100, which gives us 300. So we get this as 2 and 2 cancels out. So work done comes as our 300 joules. So option 2 is correct. Next question. It states that at 300 Kelvin, the r.m.s speed of oxygen molecule is alpha plus 5 whole divided by alpha and its square root times that of average speed in the gas. Then the value of alpha will be, use pi is equal to 22.7. So in this case, we are given, or we are going to use the formula that our Vrms is equal to 3RT upon m and its square root, and we have average speed, that is V, is equal to 8RT divided by pi times m and its square root. And according to the question, we are given that our Vrms is equal to alpha plus 5 divided by alpha and its square root times our V average, that is our V. So we substitute, we get this as our 3RT m square root is equal to alpha plus 5 divided by alpha square root, and we have this as 8RT pi m and its square root. So this square root cancels out throughout, and we get this from here, 3RT upon m is equal to alpha plus 5 upon alpha, and this is our 8RT pi times m, and this RT m cancels out. So from here we get that alpha plus 5 upon alpha will be equal to 3 pi upon 8, and we substitute value of our pi, which is given to us as 22.7. Therefore we get this as alpha upon 5 upon alpha is equal to 3 multiplied by 22, and this is 8 multiplied by 7. So this goes by 11 and this goes by 4, which gives us 33 upon 28. And now it is easy to solve. We can just manipulate it. We can write this as 1 plus 5 upon alpha is equal to 33 upon 28. So we get this as 5 upon alpha is equal to 33 upon 28 minus 1, which gives us 5 upon 28, and this 5 and 5 cancels out. Therefore we get alpha is equal to 28. So we get option number 2 is correct. Is correct. Next question. it states that the pressure and the temperature relationship of an ideal gas obeys the equation Pt square is equal to constant. The volume expansion constant of the gas will be. So we have to find out the volume expansion coefficient, which is our beta, and that beta is, or we can say can be written as, so we know that our volume expansion coefficient it is given as beta, which is 1 upon V, and we have this is partial derivative of volume with respect to temperature at constant pressure P, and we are given that our Pt square is equal to constant. This is given to us, and we also know that for ideal gas we can write that PV is equal to nRT, or from here we can write that our V is equal to nRT upon P, and so we can use this given equation, and let us assume the constant is represented as C. Therefore, we can write this will be equal to our nRT, and P will be equal to C upon T square, which gives us nR T cube upon C, which can be written as nR C and T cube. So this entire term, that is nR upon C, is constant. Therefore, we can say that our volume is proportional to cube of our temperature. Now we differentiate our equation, and differentiating such that our pressure is constant. Partial derivative, so we can say our partial derivative of volume with respect to our temperature for P to be constant, and we can get this as our nR upon C, and this will be coming as 3T square. And we substitute this formula. So we get that our beta will be equal to 1 upon V times nR upon C times 3T square, and we can substitute our volume. So we get this as 1 upon nR upon C times T cube, and multiply by nR upon C times 3T square, and here this nR, C and C cube goes by square, we have this is T cube, so this cube goes by square, so we are left with that our beta is equal to 3 upon T. So we get this is equal to 3 upon T. Option 4 is correct. Is correct. Next question. we are given a flask contains hydrogen and oxygen in the ratio 2:1 by mass at temperature 27 degrees centigrade. The ratio of average kinetic energy per molecule of hydrogen and oxygen respectively will be. So once again, we know that our average kinetic energy per molecule, average kinetic energy per molecule, that is our Ke is equal to 3/2 times Kt, and we have our 2, so we can write this as our average kinetic energy for our hydrogen, average kinetic energy for our oxygen will be equal to 3/2 K temperature of our hydrogen and 3/2 K temperature of our oxygen. So this 3/2 K cancels out and both are kept at same temperature. So therefore this temperature also goes away and this ratio comes as 1:1. So option 2 is correct. So this completes all the 19 questions from the year 2023, and all these questions were from the mains only. So in the next part we are trying to cover the remaining question of our mains for the 2023 as well as the advanced question from the year 2023. So this completes all the questions. Thank you.